Hi everybody, back to our Cook RET again. Today we will talk the basic use of our multiplexer along with our PSPICE. And then what we're going to do is we're going to use the multiplexer 74151 to design the function f with the four inputs a, b, c, d, and that equal to a complement plus bcd complement plus b complement cd. Basically, you know that you can just use the OR gate and AND gate together with the four input. But for this case, since we are going to talk about multiplexer, we're going to use the PSPICE. And when you Control G here, and you can select one of our basic multiplexer 74151, and then we're going to design the circuit here. So you look at the multiplexer here, you can see that this is going to be your output Z and Z complement. That's what you expect from your design. And later on we're going to simulate PSPICE and then see if we have our output as we want. And then for this part, is 0, is 1, is 2 allow you to have like 3 input, or you have 2 to the third combinations, or that's allow you to have like 8 combinations. Okay, so as the problem, as I mentioned, we're going to have input A, B, C, and for the D, it's going to be your something that left behind, but we will talk about that. Sorry about it. So are we gonna input this input signal ABC through the input pins of the multiplexer, which have for S0, S1, and S2. And this is what we're going to design and make a circuit connection through these pins. E is the enable, and its work. And if you apply or connect to the high level, and that's it's going to enable everything to be 0. I mean your output, but this we're going to connect enable pins to low level or digital logic 0 to make the circuit work. Okay, so that's in a general idea about the multiplexer, and this is the real one that you want to make the connection. Okay, so let's get back to our design. So how to get a start then? Well, first of all, what I have here is I have like 3 terms. So I'm gonna start by picking up a complement first and draw the Kano map, and then followed by the second terms and the third term, and put them together, and then write out the truth table to do the circuit. This is what are we going to do. So let's start with the A prime here. So I have input A, B, and CD. A are 0, 0, 1, 1, and B are 0, 1, 1, 0. And for the and Z, you do the same thing, right? So 0, 0, 1, 1, and 0, 1, 1, 0. Now the first term are a complement. We just take a look at which one the skip a complement, which is the logic 0. So we have the logic 0 here for A input, and that's why you look through the right. So I'm going to have put like 1 1 1 1 here, and also I have a complement here. I still also have 1 1 1 1 here. So that's why I end up with the kind of map like this. Okay, we don't care about our D, C, or B. We just care about our A complement. Next step, we're going to take a look at the B, C, and D complement. This is my B, C, D complement. It's a little bit tricky here. Okay. So before we have a complement, so you need to bring that down here, as well. That's why I still have 1 1 1 1 1 1 1 1 here. But now the next step, the reason I do that because here is nothing to do with the D input. So that's why I bring this down here. The same thing as if you look ahead for B complement and C D, and this one have D, but you still need to bring down a complement down here. That's why I still have 1 1 1 1 for the third term, right? This is the second term. Now what you need to do is you need to take a look at the B, C, D complement. And this is my D complement, right? This is my D complement. And then where is B and C? This is my B, and this is my C. But you need to look straight down here, and this is become our C and D complement. And you also need just only B, right? And you already have one here, so you don't have to take a look at that. But you need to look at B become just 1. So I have 1 show up here. Okay, try it again. So what about the term B complement and C and D? As I mentioned earlier, that you still have to bring up A prime because it's nothing to do with D, right? So you already have this term, the same thing. But where is the B complement and CD? This is my CD, right? So you look down here. And where is my B complement? This is my B complement. So that's why I have one right here. So this is the B complement, and this is the CD. Alright, so we already have our kind of maps for 3 terms from the problem here. The next step is you need to include everything in the single kernel map. So I end up with the kernel map like this. This is come from a prime, right? Or a complement, and I have this term here. I have 1 from this term, and this one here I get it from this term. Now the next step is to write the truth table. I also need to point this out for you as well, because it's a little bit tricky. Sorry, but sorry. Well, I have my input select and I have output. So I have our input select from a multiplexer to be S2, S1 and S0. You take a look back at your multiplexer here. You have S0, S1 and S2. So it's going to become input A, B, C, right? Of the multiplexer 74151. Now let's get back to the truth table. How I came up with the truth table like this. This is my inputs select S2, S1 and S0. So I don't care about input D. I have only C, B and A. For EN is the enable pins of the multiplexer and it's work on high. So that's why I connect. We're going to connect enable pin to the low level input or digital logic low or 0. Whenever enable to be high, it doesn't care, you know, what kind of have CBA is going to be, but are going to keep you the output to be low for Y, right? And then I just wrote this down as the output, and for W is going to be actually is become a Y complement. So whenever you have low here, you're going to have high here. You have 1, you have 0 here. You have 0, you have 1 here. Okay, nothing to worry about too much. Well, the first step you need to write down for C. It's going to have since you have 3 inputs, you have 2 to the third combination, so that's give you 8. So that's why I have C start from 0, 0, 0, 4 zeros and then 4 ones. For B I have 0, 0, 1, 1, 0, 0, 1, 1, and for A I have 0, 1, 0, 1, 0, 1, 0, 1. Okay, so you already understand about this part of the truth table. Now take a look at the output Y here. Well, you take a look at the CBA to be your 0, 0, 0. So you take a look at C, you have 0 here for C, right? And also B and A become 0, so you have only this part. You look at this one here, and you look at this one here. So that's mean you're going to pick up 1 and 1. So that's why I have our Y output to be 1 here. Okay, let's try again. What about our 0, 0, 0, 1? C is 0, 0, and then B is 0, 1 is right here, right? And this is your C here, 0, 0. So 0, 0, 1 just give you what? You look down here, and you look from the left to the right, so you pick up this one. It simply becomes 0, correct? So that's why I put 0 right here. And then this one I'll start from D0, D1, D2, D3 until D7. Okay, just start from 0, 1, 2, 3. Now let's take a look at what? 0, 1, 0. So this is 0, 1, 0 is here because you talk about CBA, right? 0, 1, 0. You do the same thing. Just come down here. You have our output to be 1, so that's why I put 1 here. Okay. Alright, you probably get some idea about how to draw the truth table, but let's take a look at this one here. D. You have our input CBA to be 1, 0, 1. Now take a look. 1, 0, 1. This is C is 1. Where's my 0, 1? My 0, 1 here, right? You look down here, you look from the left to the right, you end up with this one. the number is not the same, right? It's not 1 1 or 0 0. So you look at the D, it's look exactly just like D 1 0, and this is 1 0. So that's why I put D down here. Okay. So what about the prime or the complement then? CBA or input, they all have like digital logic 1. You look at the 1 for C, and A and B is 1. You look from the left to the right, from the top to the bottom here, you have 0 1, and it's simply become a complement of D. That's why I have the complement right here. Okay, so finally you have a truth table, and be ready to do the design of the PSPICE. So for W, as I told you before, it's just become a Y complement. You have 1 for Y, you have W to be 0. You have D for Y, you have D complement for W. Okay, this is the how to do the design. The next step is, let's go to PSPICE. What happened, I have for the multiplexer here. How I'm going to make a connection. Well, I already have just to save the time, and I already have the complete circuit for you here. Okay, let's take a look together. Let's see if I can compare two windows together. Probably alright, this one is give you a better views. So the last step, that we have a truth table. So what we're going to do is, as I told you before, you have S0, S1, S2, and S2 becomes C, right? And S1 become input B, and S0 input A. And then for enable here, to make it works, I connect enable pins to ground or digital logic 0. That's why I have ground here. So I have the E enable pin here. And what else? Well, you take a look at the for digital logic 1 or high, right? These are high. So I need to connect D0, D2, D4, D6 to all together, and connect to digital logic high or 1, right? Let's do 2, 0, 2, 4, and 6. 0, 2, 4, and 6. See that? You know, I have these pins are connected together, and then I connect this one to digital logic high or 1. How do I do that? For the clock, you can simply connect to the supply 5 volts, but this one I use the digital clock, DIG CLOK, and then what you need to do is I said this one is never be off time, right? It's just like on time all the time. So let's give the logic, digital logic 1. Or you can use the only, as I told you, or VSRC supply to be your FIFO. That's what we do as well. And now what? For output to be 0 here, they are 0. So you take a look at D1 and D3. From here, D1 and D3. Just connect together and connect to the ground to give your digital logic to be 0. Okay. Now what about the rest? You have our D5 with the input logic to be 101, and at D5, right, you expect output to be D, so that's why I also have D input here. That's why I connect D5 to input D. But for the complement at D7, I have D7 here. The complement, I just put the inverter, so invert everything, of the D to be the complement and input to I7, or at the address D7. You probably get some idea, right, how this one's work. I mean, how to do the circuit connection here. Okay, let's take a look at the PSPICE. Now to design the clock. Since it seems to be it looks like we have only 3 inputs, but in this case I also have our input D. So I'm going to set up the clock signal to have our all combination for the 4 inputs. I start with the A, or you can say the least significant bit. So this one have the period. I'm going to start to be minimum period. So that's why I put 0.5 microsecond, or the period is 1 microsecond, right? What about B? Since let's see here, this is the clock of A, right? And I want to have the OR combination, so for the B, I would have the period to be twice or double of the period of A, and as well as C. The period is going to be double of B, and D, the period is going to be double of C. So you probably get an idea about what I'm going to do here. For the period of A to be 1, right? For B, I would have the period to be 2. That's why I have on time here 1 microsecond, and off time here to be 1 microsecond, or the period to be 2 microsecond. And for C, definitely I'm going to increase the period to be 4 microsecond. Okay, you break it out to be on time 2 microsecond, and off time to be 2 microsecond. The same as D. You're going to have the period to be 16, right, microsecond, double period time of C. That's why I break it up to be on time 8 microseconds and off time to be 8 microseconds. Okay. Now you need to go to setup, ready to see the plot or the output waveform. The maximum period here I have like 16, right? And microseconds. So the final time, that's what I need, is the 20 microseconds. So that's more than enough. Or you can increase, the final time, whatever you want. So now I'm ready to simulate, but I have to delete this one first. Go to analysis, then you go to simulate. Okay, then now you want to go to the plot. Okay, let's see what we want to plot. I want to see the input signal A, B, C, and also D. That's what we concerned, right? A, B, C, and D, and I want to see the output Z. Make sure that it corresponds to the truth table that we already designed, or give us the output here. The function is to work is here. Okay, now let's go to add the plot. You start with the A, add input B, add input C, and then add input D. And now you want to see the output, which is the U1Z. This is your output. So it's look like this. Now it's going to be the time you want to check your design. Okay, let's blow this up a little bit and bring the truth table up. Now let's see if we have the right output. Okay, I'm going to bring up cursor, right, to help us to see your digital logic at each stage. Okay, so let's start with the input 0, 0, 0. Supposed to get output to be 1, right? Or at the address D0. Now where is the 0, 0, 0? Well, you look at this one, 0, 0, 0. Waste. This is input ABC. I have right here, right? 0, 0, 0. And then this is your output. So it's already give you this is your input ABC, right? And this is your output. It's supposed to give you 1, right? This is your output 1. Okay. Let's check this is start from A. Right. Let's look at the 1. So let's take a look at the 0, 1, 1. Also gives you the output to be 1, right? Where is 0, 1, 1? This is 0, 1, 1. Correct? Also give you our output to be 1. And what about our 0? I mean your output 0. Let's pick up this one here. So I have our 1, 1, 0. It's supposed to give your output to be 0. Where's 1, 1, 0? This is my 1, 1, 0. Correct? 110 and give you output to be 0. And now what about our D? Okay, we also want to check, let's see your D. You have our 101. It should give you D, right? So let's find 101. This is 101, right? 101. And does that give you D? 101. This is your D. Your D is 0, and your output becomes 0. So it's correct, right? Now let's take a look at the, what about the prime or the complement? Oops, sorry. This is the complement. When you have input 111, they're all high, right? So let's take a look at the 111. Do you have somewhere here 111? Yeah, this is 111, right? So your D input is 0, and you have a D complement as output, so that's why you have 1 here. Okay, so this is just the simple or the basic design using the microcontroller. I think you can have some idea about that. And you check this function here. If ABCD is going to work, you know, just like you design the truth table. So it's good for you to have, you can verify your design by PSPICE. It gives you a beautiful output waveform with that corresponds to whatever you design, corresponds to the truth table. Okay, I'll see you in the next YouTube.